Okay, we're going to talk about exponential growth and decay. And first of all, you may have heard a thing about a chessboard where you collect $1 a day, or over a month you collect $1 and then it doubles to $2 and to $4 and $8. And eventually at the end of the month, would you like that, or would you just like $10,000 a day or something like that? And when you've seen that, you often find that you end up with these huge amounts of money because this doubling effect is very huge. And so first of all, if you've got a series like this, which looks like it's increasing very rapidly, it's not linear because I'm not adding the same amount every time. This is what's often called an exponential series or a geometric series because I'm multiplying by something every time. And in this case, it's very easy to see that I'm multiplying by 2 every time. But if I don't see what's happening, I just notice that it's advancing rapidly and it's not evenly spaced, very often I can figure out what's the multiplier simply by dividing one term by the previous term. So like if I grab those two, I could do 8 divided by 4, and that gives me 2, or any one of them. So that's how I find my multiplier, and that's really important. Now what's really going on here is if I want to figure out maybe what do I get at the end of the month. If somebody makes this agreement with me, I'm going to pay you $1 on the first day and $2 on the next day and $4 on the next day. What am I going to get at day, 31 if this is day 0? So if this is day 0, which is often the way we start, just to make it easy, the question is what happens at day, the 31st day, which actually we'll call day 30. Because this is day 1, this is day 2, this is day 3. And so we could go through all these and double and double and double and double and double, but there's a quicker way because there's a pattern going on here. And basically, if you think about it, in the first day I get $1, the next day I get 1 times 2, the next day I get 1 times 2 times 2, the next day I get 1 times 2 times 2 times 2. So you can see a pattern developing here. So this is the first day, this is the second day, this is the third day. On the fourth day, I'm going to get 1 times 2 to the fourth, and so on. If you actually think about this, on the first day, I actually get 1 times 2 to the 0, because anything to the 0 is 1. And so we just continue that pattern. So it's very easy to me to figure out that on day 30, I'm going to get 1 times 2 to the 30. And I can put that in my calculator. And this comes out to roughly roughly $1 billion. Forgotten the actual number. I had it in my calculator a minute ago. Yeah, it's roughly $1 billion. I'm just going to say 1 billion. $1 billion. It comes out a very large amount because this doubling effect is very aggressive and things add up really quick. And we'll talk about on the graph, this looks like a very steep curve. It starts out slow, but then it gets very steep. All right, so that's the idea. That is exponential growth. So let's talk about exponential decay. A problem you might have for that is something like this. I've got a pool that's draining, and maybe because of the effects of gravity, it doesn't drain quite as much every time, so it only drains at what's called a 20% rate. So every time it's going to drain at 20%. And I know that because based on these numbers, I kind of jumped right over to that, 80 divided by 100 800 divided by 1,000 is going to be 80%. And 640 divided by 800, if we're being consistent, is also going to be 80%. And you're like, well, how did you get 20%? I'm getting a little ahead of myself, but this is actually a decrease of 20%, or it's doing 80% each time. If I'm getting 80% each time, I'm actually decreasing by 20%. We'll come back to this. So the question is, what happens at 10? Well, the same pattern is happening that I saw before. I'm multiplying times 0.8. I'm multiplying times 0.8. So that times 0.8 is the next one, and that one times 0.8 is the next one. And so essentially the same thing we saw in the last one. The equation here is the number of gallons in the pool. The gallons is equal to the original amount, which is 1,000, and it's going to be times 0.8 for every hour. And I don't know if I actually explained that very well what was happening here, but basically every hour I get 80% of the previous amount, and I started with 1,000 gallons. So that would be another example, and there would be the formula for that. So when we have this geometric growth or decay, if we know the multiplier, we can say, oh, I can find, for some number, for the number of periods or the number of times I'm doing this thing, what is it at that point? So it's a very quick way for me to doing this as opposed to doing times 0.8, times 0.8, times 0.8, times 0.8. Just speed things up. And we've also talked about in class, for those of my students who are watching, a quick way to do this as well. If you put it in a graphing calculator, look at the table, and you can quickly get these values and say, okay, what happens at 10? But for 10 here, I would just do 1,000 times 0.8 to the 10th, and I'd figure that out. And that would be it. Actually, that was the number I got before. I was confusing myself with my notes here. This ends up being roughly 107 gallons after 10 hours. The other thing was also a billion, but I was getting some of my numbers mixed up. Okay, so there's that. Let's talk about some problems you might get. So an investment of $100 increases by 6% per year. What's the year at the year 20 value? So once again, this is where you have to remember that if you actually multiply the 20 times 0.06, which is what 6% is, that number gets smaller. I'm sorry, the 100 times the 0.06, that number actually gets smaller and smaller and smaller. This is where you have to remember this little trick. When you're talking about a percent increase or decrease, you have to take 1, which is the initial amount, and then add or subtract whatever the increase or decrease. This is an increase, so I'm going to add 0.06 onto it. So my multiplier is 1.06. And if this was a decrease, it would be a 0.94 because I'm actually going to take my original amount and make it a little smaller every time. But this is going to basically take my 100, preserve it, and then the 0.06 is going to make it a little bit bigger, a little bit bigger, a little bit bigger. So my formula is y equals whatever I started with times my multiplier raised to the x. And so I can very easily just take my calculator and plug in 100 times 1.06 to the 20th. And that has the exact same effect as me taking the 100 and multiplying times 1.06 times 1.06 times 1.06 and going all the way down. And notice also at year 0 or at time 0, that's going to go to 1 because anything to the 0 is 1, and so that's my initial amount, and that completely makes sense. Okay, but sometimes I'm given a table. It's less rare. It's more rare, actually, for me to get a table. But I can try to figure out the formula here. And once again, this is back to our pattern, is for whatever the formula is, assuming this is exponential, I can just divide this by this, 95 over 100, or if it's consistent, I can divide the 90.25 over 95. Now these tables, these have to be 1 apart for this to work this way, but either way, when I do that, I'm like, oh, this is a multiplier of 0.95, which actually would correspond to a 5% decrease, because we'd take the 1 and we'd subtract the 5%. And then so the formula is simply, well, what did I start with? I started with 100, and then every time I am multiplying times 0.95, and then so at some point in the future, if I wanted to know, like at 0.5 in the table, I could just put whatever 5 is, and it would automatically figure out for me, oh, that's like multiplying times 0.95 5 times, and that completes my table. All right, and then another kind of problem you might get is one where you actually don't know the rate at all. All you're given is like an end point and a beginning point. So in this case, a population starts at 12, so that's my starting point is 12. I'm going to use P instead of Y here. Population is going to be 12 to start with. I've got some rate, and so I'm going to just call that, I don't want to call it X. I'm going to call it, what do I have here? Let's call it V. I'm going to call it V for no particular reason except I had a slash there. And 8 periods. I'm saying periods because this could be days, weeks, months, number of times something happens. But 8 periods later, it's going to be that. And actually, I know the population here. The final population is actually 15, so I didn't need to use the p there. I do 12 equals v to the 8, and I'm running out of room here. And I've got a little dismissed battery thing on my phone. So now I'm getting, this is really looks like a power function, which we've looked at before. So the way to find out the answer of what this thing is I divide the 12 by the 15. I get 15 twelfths, or whatever that happens to be. I worked this out already. Equals v to the 8th. And then I'm going to undo that by raising 1 to the 8th on both sides. And this essentially works out to 1.03. And the important thing to remember about, because of the way I set this thing up, this v here is actually the multiplier. So maybe I should have called that m. So the actual rate here is actually 0.03 or 3%. Okay, so that's an important point to remember there. Okay, getting close to the end here. We start graphing these things. You should recognize that all these, and I mentioned it before, all have this hockey stick shape. It's either going left or right. If we've got a number that's bigger than 1, it's going to be increasing. It's going to be exponential growth. For all those, they will go through 0, 1. And they will also go through 1, comma, whatever the base is. Okay, so anything bigger than 1 will have this. Some will be steeper than others. And then if it's some number less than 1 but greater than 0, it will also go through 0, 1. And once again, the reason for this is anything to the 0 is 1, so that happens on both of them. And this also goes 1, comma, whatever the base is, because that thing to the 1 is going to be that number. But that's one thing to notice about this. It's a little different than some of our other formulas, is the value of that determines whether our hockey stick is kind of a right-hand hockey stick or a left-hand hockey stick. And then finally, for those of you who've done transformations before, I'm doing this very quickly. The rules are exactly the same. The only difference is outside stretch, the up-down stretch, vertical stretch is going to be the number out front of the b. The up-down translation is still added on to the function. This is the function. And then the thing that's a little different about this one is for the side-to-side translation, the inside the function is the exponent. So if I take the exponent and add something onto it, it translates it to the left. Or if I minus something on it, it translates to the right, because we know inside the function is kind of backwards. And then we rename this thing W. Typically we've used a B there, but we already call our base B, so we rename this W for width. And so that's our side-to-side stretch. And I'm going to show you just a couple examples online, and I'll be done. All right, so we're going mobile here. All right, so here's a picture we've got here. This is the parent function, y equals 2x. Now, once again, anything that is greater than 1 will kind of have this shape, but this is specifically 2x. And then I've just got a couple of things I want to show you here. So if I multiply out front, you can see that, oh, that's been stretched. And one thing that's important to notice here is this is over 1 up 1 in the parent function. It's over 1 and up 3 in the child function. So that's why the 3 out front does that. In the same way, I've got another one here. Once again, over 1 and up 1 in the parent function. This is over 4 and up 1 in the child function. So that's a stretch in the horizontal direction, and that's why that ends up being probably a little out of focus here. There we go. That is 2x to the 4th. Once again, that other one, in case you didn't see it before, that's stretched in the other direction. Yeah, the focus is a little better now. We can also I'm doing this kind of in a granular fashion. If I subtract 2 from the original function, so that's 2x minus 2, you'll notice that the shape stays the same, over 1, up 1. I can tell it hasn't changed, but everything's shifted down 2. If I subtract from the inside of the function, which is x minus 2, notice it's up in the top there. Put it inside the function, which makes it x minus 2. You'll notice that, did I turn it on? I didn't turn it on. This is, I didn't put the points in here. But that point right there is now that point right there, and that point right there is now that point right there. So everything just shifted over to, but the shape stayed the same. And then finally, the last one that kind of combines a little bit of everything is, where is it? There we go. This one right here, if you actually look at the formula, you will see I've done a stretch 3 minus 5 divided by 2 minus 4. So that's very difficult for you to see. Let's zoom in there. Okay, so notice the minus 5 and the divided by 2 are in the exponent, and the minus 4 is on the outside. So what this does over here is takes that original point, let me focus again, takes that original point, moves it down 4. Is that right? Well, this is a little hard to tell. So let's look at the stretch first. It's the stretch is over 2 and up 3 compared to our original. So that's where the 2 in the bottom comes from and the 3 outside comes from. And then it is a little bit difficult to tell that this thing is actually minus 4. Because of the stretch, it's all relative to this asymptote. So maybe this wasn't a great example to show last. But that kind of combines a little bit of everything. We typically don't throw all those in. Oh, there was one more. I forgot. We can still do flips. I've got it in here. Where's my flip? There's my flip. So this is one that's flipped, and you can see, oh, yeah, that one's flipped. It's not changed at all, and so that's just a negative out front. So all our rules apply, and that's actually really important because I didn't mention that earlier. That's way more than enough. Hopefully that helps. Ciao.